So what if the future of AI isn't about getting bigger and bigger, but about getting smarter and way, way more efficient? Today, we're going to dig into this really fascinating paper called the Spiking Manifesto. It's proposing a totally new direction for artificial intelligence, and it's all inspired by the most powerful, most efficient computer we know of, the human brain.
All right, to kick things off, let's just look at a comparison that is, well, it's pretty wild. On one side, you've got a top-tier AI model like Llama 3, chugging along on tens of watts of power. And on the other side, the human brain. It runs everything, your thoughts, your feelings, your senses, the whole shebang, on just 20 watts. I mean, think about that for a second. Our very best AI is already burning more power than our brains, and it has thousands of times fewer connections.
And if that didn't already blow your mind, get this. The paper points out that if you actually scaled the brain down to the same size as Llama 3, it would only need 2 milliwatts of power. That is so ridiculously small, you could power it for a whole month with one of these, a single AAA battery. We're not talking about a small difference here, we're talking about a 1,000-fold gap. So the real question is, how on earth does the brain do it?
Well, according to the manifesto, it's not one thing. The brain has two fundamental secrets that just leave our current AI completely in the dust. Let's break them down.
Here they are, the brain's two big tricks. On the left, you've got efficient processing. See, unlike AI neurons that are always on, always calculating, our brain neurons are mostly, well, they're silent. They only fire a single sharp spike of energy when it's absolutely necessary. It's this all-or-nothing event that saves a massive amount of power. But the real magic, the absolute genius, is on the right, efficient encoding. Current AI basically just cares if a neuron fires. The brain, though, it cares deeply about when it fires. The super precise timing and order of every single spike is what encodes this unbelievable amount of information.
To really get a feel for that encoding power, just imagine 60 neurons, only 60. If you only care that they fired, that's just one bit of data. But if you care about the exact order they fired in, well, the number of possible patterns is 60 factorial, which gives you this number, a number bigger than 10 to the 80th power. Let me be clear, that is more than the estimated number of particles in the entire known universe. All of that information from the timing of just 60 little spikes. It's insane.
Okay, so the brain is ridiculously efficient. How in the world do we get our AI to do that? Well, this manifesto proposes a complete paradigm shift. It's about moving away from the brute force, heavy-duty matrix multiplication that powers all AI today and moving towards something much simpler, much more elegant. And this table just lays it all out, plain and simple. Current AI, what we call ANNs, thinks in terms of firing rate. It's a continuous value. And its main job, its core operation, is matrix multiplication. That's why we need those giant power-guzzling GPUs. But this new brain-inspired AI, the SNNs, they don't care about rate. They care about the latency of the spike, its timing. And its core operation, forget multiplication. It's something you learned about in grade school. Look up tables.
And this, right here, is the central claim of the entire paper. I'll just read it. The claim is that spiking networks are nature's way of implementing lookup tables. So instead of doing this massive calculation from scratch every single time, what if the brain is just looking up the right answer based on the unique pattern of signals it receives?
Okay, that's a huge idea, right? The brain is a giant lookup table. But how would that even work? How do you turn a messy, complex pattern of spikes into a simple, clean lookup?
Well, the process is actually way more straightforward than you might think. It really just boils down to 4 steps. First, assign. You just link up some random pairs of input neurons. They call them anchors, to a lookup table. Second, compare. As the spikes come in, you do a simple check. Did neuron A fire before neuron B? It's a yes or a no, a 1 or a 0. Third, concatenate. You take all those 1s and 0s and string them together to make a unique number, an index. And finally, step 4, select. That index points you directly to a specific row in your table, which already has the answer waiting for you.
And here you can see it all come together. You've got this pattern of spikes coming in. By just comparing the timing of a few of them, those anchors, you create a binary code, like 011. That code is basically a key. It instantly unlocks one specific row in a table to give you the output. And here's the most important part. There's no heavy-duty, power-hungry multiplication anywhere. It's just a direct, super-fast retrieval.
So we've seen the how, but what about the why? Why go through all the trouble of rethinking AI from the ground up? Well, the potential payoff is, and I'm not exaggerating, nothing short of revolutionary. Now here is the most brilliant part. You don't have to throw away decades of AI research and start from scratch. Instead, you can take the core engine of today's models, that power-hungry matrix multiplication block, or MatMul, and you can literally just swap it out. You replace it directly with this new, hyper-efficient lookup table block, the LUT. It's like taking the gas-guzzling engine out of your car and dropping in a tiny, powerful, incredibly efficient electric motor.
And what's the result of that swap? The paper makes this absolutely incredible claim, offering the promise of a 1,000-fold improvement in performance. Let me just say that again. 1,000-fold improvement. Not 10%, not 100%, 1,000 times better. That is the kind of number that just changes the entire game.
So what does 1,000 times more efficiency actually get us in the real world? It could unlock a completely different future. We're talking about a whole new class of AI hardware built specifically for these lookups, finally moving us past the GPU bottleneck. It means radically lower energy cost, which could actually make AI sustainable on a global scale. It means having powerful AI that can run on your phone, not just in some giant data center. And really, it just gives us a path forward that can actually keep growing.
And so that leaves us with this one huge question to think about. We've all seen the amazing things today's AI can do with its powerful but pretty brute force approach. But what becomes possible when the tools we're building are 1,000 times more efficient? What new problems could we solve? What new worlds could we build if the fundamental cost of intelligence just drops off a cliff? The brain has already shown us the path. The real question is, are we finally ready to follow its lead?